27,000 feet above Schweinfurt, Germany. August 17, 1943. Captain Walter Cook rolled his P-47C Thunderbolt inverted and pointed the nose at the earth below. Through his canopy, he could see the Messerschmitt Bf 1-10 twin-engine fighter climbing confidently toward the B-17 formation, its crew completely unaware of the physics equation that was about to destroy them. Cook pushed the throttle forward. The massive Pratt & Whitney R2800 engine responded instantly, but something else was happening deep in the fuselage behind him, something the German pilots had never encountered, something that would fundamentally alter aerial warfare. Exhaust gases from 18 cylinders were being channeled through complex ducting along both sides of his cockpit, driving a General Electric turbine spinning at over 21,000 revolutions per minute. That turbine was compressing thin air at altitude and forcing it back into his engine, maintaining sea-level power where other fighters gasped for oxygen. The airspeed indicator began climbing, 400 miles per hour, 420, 450. Cook's P-47 was accelerating through velocities that would tear the wings off any German fighter attempting to follow. At 480 miles per hour, he squeezed the trigger. 8 Browning 50 caliber machine guns converged their fire on the Bf 1-10. The German aircraft disintegrated. Before the wreckage even began falling, Cook pulled back firmly on his control stick. The massive Thunderbolt, now carrying kinetic energy equivalent to millions of foot-pounds, converted all that speed into vertical climb. Within 40 seconds, he was back at 26,000 feet, repositioned above the fight, ready to dive again. The German pilots who witnessed this maneuver radioed back to their commanders with reports that seemed impossible. American fighters were diving at speeds exceeding 500 miles per hour, remaining completely controllable, then climbing back to altitude faster than pursuing German fighters could follow. The Luftwaffe's tactical doctrine, built on 4 years of successful combat experience, offered no counter to this capability. They didn't understand what they were fighting. They didn't know about the turbocharger, and that ignorance would cost them air superiority over Germany. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how American engineers created a fighter that could dive 550 miles per hour and recover safely begins not in combat, but in a Long Island factory where Georgian immigrant Alexander Kartveli was solving a problem that had stumped every other aircraft designer in the world. How do you make a piston engine produce maximum power at 30,000 feet, where the air is so thin that conventional engines lose more than half their horsepower? The answer was the turbo supercharger, a technology that had existed since the 1920s, but had never been successfully integrated into a frontline fighter aircraft. Kartveli's genius was not inventing the turbocharger. His genius was building an entire fighter aircraft around it, accepting weight penalties and complexity that other designers rejected, creating a machine that would prove revolutionary in ways even he didn't fully anticipate. The General Electric B-Series turbo supercharger that powered the P-47's high-altitude performance was a masterpiece of mechanical engineering. Mounted in the rear fuselage beneath the tail, this device captured exhaust gases from all 18 cylinders of the R2800 engine. Those gases, still containing enormous thermal energy after driving the pistons, were piped through insulated ducting that ran along both sides of the cockpit. This ducting had to withstand temperatures exceeding 1200 degrees Fahrenheit, while maintaining structural integrity during violent combat maneuvers. The exhaust gases struck the turbine wheel, a precision-machined component that spun at speeds up to 21,300 revolutions per minute at full combat power. To put this in perspective, this turbine wheel was spinning at 355 revolutions per second, fast enough that centrifugal forces created stresses that pushed contemporary materials science to its limits. Republic Aviation had to use special high-temperature alloys developed specifically for this application. The turbine drove a centrifugal compressor on the opposite end of the shaft. This compressor drew in ambient air, compressed it to higher pressure, and forced it through an intercooler system before feeding it back to the engine's integral supercharger for final compression. The intercooler was crucial. Compressing air heats it significantly, reducing its density and potentially causing detonation in the engine. Cylinders. The intercooler, using ram air from flight speed, cooled the compressed air back down, increasing its density and allowing the engine to produce more power safely. This two-stage compression system, turbocharger plus engine-driven supercharger, allowed the R2800 to maintain 2,000 horsepower up to 27,000 feet. At 30,000 feet, where German fighters were losing 30 to 40% of their sea-level power, the Thunderbolt was still producing over 1,800 horsepower. This altitude advantage was significant in level flight, but it became absolutely decisive in dives. The physics of diving at high altitude with turbocharged power created capabilities that German pilots found incomprehensible. When a P-47 at 30,000 feet rolled inverted and dove, gravity accelerated it downward while the turbocharger-fed engine continued producing nearly full power, adding thrust to gravitational acceleration. German fighters diving from the same altitude without turbochargers lost engine power as they descended, because their engines were optimized for lower altitudes and became overboosted in denser air at lower altitudes, forcing pilots to reduce throttle. The P-47 pilot could keep his throttle firewalled throughout the dive. The automatic wastegate system on the turbocharger regulated boost pressure, preventing overboost conditions, while maintaining maximum safe power output. This meant the Thunderbolt was accelerating under both gravity and continuous engine thrust, while German fighters were accelerating under gravity alone with reduced or idle engine power. From 30,000 feet, a P-47 diving at full power could reach indicated airspeeds of 500 to 520 miles per hour within 15 to 20 seconds. Under optimal conditions, with extended dives from very high altitude, some pilots reported indicated airspeeds approaching 550 miles per hour, before encountering compressibility effects that limited further acceleration. These velocities created closing speeds that made evasion nearly impossible for enemy fighters. If a German pilot in a Bf 109 or 4U 190 was flying at his aircraft's maximum speed of approximately 380 miles per hour and a P-47 dove on him at 500 miles per hour, the closing speed exceeded 120 miles per hour. At this closure rate, the German pilot had approximately 3 seconds from first sighting the attacker to impact. Most human reaction times couldn't process the threat fast enough to initiate effective evasive maneuvers. German fighter pilots, trained on aircraft where high-speed dives were dangerous due to structural limitations and control problems, initially assumed American pilots diving at these velocities were suicidal or desperate. They expected to see Thunderbolts tumbling out of control or breaking apart from structural failure. Instead, they watched American fighters dive, fire devastating bursts, then pull out smoothly and climb away. The psychological impact was profound. What the German pilots didn't know was that Republic Aviation had invested enormous engineering effort into making high-speed dives survivable and controllable. The key was in the wing design and structural strength. The P-47's wing used a semi-elliptical planform with relatively thick airfoil sections, particularly near the root. This thick wing design, which made the Thunderbolt inferior in turning performance compared to thinner-winged fighters, had a crucial advantage in high-speed flight. Thick wing sections delayed the onset of critical compressibility effects. As an aircraft approaches the speed of sound, airflow over certain parts of the wing, particularly where the surface curves most sharply, can locally exceed sonic velocity, even though the aircraft itself is flying subsonic. When this happens, shock waves form, dramatically increasing drag and potentially causing severe control problems. Thinner wings with sharper curvature tend to reach these critical conditions at lower speeds. The P-47's thick wing, combined with its relatively straight trailing edge and lack of sharp curves, allowed it to reach higher speeds before encountering severe compressibility. Wind tunnel testing and combat experience showed that the Thunderbolt could safely dive to approximately 0.85 Mach number, roughly 520 to 540 miles per hour, true airspeed, depending on altitude and temperature, before experiencing serious compressibility effects. Even when compressibility occurred, the P-47's massively strong structure and large control surfaces meant the aircraft remained recoverable. Pilots reported that around 500 to 520 miles per hour indicated the controls would stiffen significantly. The stick required much more force to move. The aircraft would develop a tendency to tuck, pitching nose down more steeply. But if the pilot maintained firm back pressure on the stick without over-controlling, and most importantly, never touched the trim tabs during the recovery, the aircraft would descend into denser air, where compressibility effects diminished, and the controls would gradually become effective again. The critical recovery procedure, taught to every P-47 pilot and documented in the official pilot's operating handbook, was specific and counterintuitive. When encountering compressibility, maintain steady back pressure with both hands on the stick. Do not adjust trim tabs under any circumstances. Do not attempt violent control inputs. Simply hold firm back pressure and wait for the aircraft to descend into denser air. As air density increased below approximately 15,000 feet, compressibility effects would naturally dissipate, elevators would regain authority, and the pilot could complete the pullout. This procedure worked because of the P-47's structural strength. The wing spars could withstand loads exceeding 8G positive, far beyond what the human pilot could endure. Even during high-speed recoveries where the pilot was experiencing 6 to 7G and graying out or briefly losing consciousness, the airframe remained intact and continued pulling out of the dive. Some pilots reported regaining consciousness to find themselves already back in level flight, their aircraft having completed the recovery automatically while they were briefly incapacitated. German pilots attempting to follow P-47 seconds into these high-speed dives discovered their aircraft had no such safety margins. The Bf-109's maximum permissible dive speed was approximately 460 miles per hour indicated, beyond which structural failure became increasingly likely. The WWII had better dive characteristics but was still limited to approximately 450 to 470 miles per hour. Neither aircraft could safely reach the speeds that Thunderbolts routinely achieved. More critically, German fighters lacked the control authority at high speeds that the P-47 possessed. The Bf-109's elevator became extremely heavy above 400 miles per hour, making recovery from steep dives physically exhausting and time-consuming. The WWII handled better, but still required significantly more altitude to complete recovery than the P-47. German pilots had to begin their pullouts at higher altitudes to avoid hitting the ground, giving them less time in the attack and making them vulnerable to counterattack during the extended recovery. The turbocharger provided another decisive advantage during the recovery phase. As the P-47 pulled out of its dive and transitioned from descending to climbing, the pilot could maintain full throttle. The turbocharger would automatically adjust to maintain optimal boost pressure as altitude changed. This meant the Thunderbolt could use both its accumulated kinetic energy from the dive and continuous engine power to zoom climb back to altitude. The zoom climb was perhaps the most tactically important phase of the entire attack sequence. After firing on a target at lower altitude, typically between 15 and 20,000 feet, the P-47 pilot would pull approximately 4 to 5G to convert his airspeed into altitude gain. At 500 miles per hour, at 20,000 feet, the Thunderbolt had kinetic energy that could theoretically lift it approximately 3,000 feet higher if perfectly converted. In practice, accounting for drag and continued engine power, a properly executed zoom climb from 20,000 feet at 500 miles per hour would return the aircraft to 27 or 28,000 feet within 40 to 50 seconds. During this zoom climb, the P-47 was extremely difficult to attack. It was climbing at angles approaching 30 to 40 degrees nose up, moving too fast for German fighters to catch from behind, and too high an angle for deflection shots from the side. By the time any pursuing enemy fighter could maneuver into firing position, the Thunderbolt was already back above the fight, repositioned for another attack. German fighters attempting the same maneuver faced insurmountable disadvantages. Starting from lower altitude without turbocharged power, they had to climb the entire distance using engine power alone. At 20,000 feet, a Bf-109's engine was producing perhaps 70% of its rated power due to altitude effects. Climbing from 20 to 30,000 feet required 4 to 6 minutes of sustained climb, during which the pilot was vulnerable to attack and consuming fuel rapidly. The tactical implications revolutionized fighter doctrine. Traditional fighter versus fighter combat since World War I had emphasized turning ability. The fighter that could turn tighter would eventually get behind his opponent and shoot him down. This doctrine assumed roughly equal starting conditions, similar altitudes, and aircraft with comparable performance. The P-47's turbocharger-enabled altitude advantage and diving speed broke these assumptions completely. American pilots never had to turn. They maintained altitude superiority, dove at speeds no enemy could match, fired quick bursts with overwhelming firepower from 850 caliber machine guns, and recovered to altitude before the enemy could respond. If German fighters tried to climb to meet them, the P-47 seconds simply climbed higher, always maintaining the altitude advantage that made their diving attacks possible. Major Francis Gabreski, who would become the top-scoring American ace in Europe with 28 victories, all achieved in P-47 seconds, described the tactics in post-war interviews. "We owned the sky above 25,000 feet. The Germans couldn't effectively fight us there. Their engines were losing power. Ours were still producing maximum output thanks to the turbocharger. Once we were above them, we could attack repeatedly. Dive, shoot, zoom, climb, dive again. They couldn't catch us diving. They couldn't follow us climbing. They couldn't run away because we were faster. The turbocharger gave us an advantage that no amount of German pilot skill could overcome." Lieutenant Robert Johnson, who survived one of the most damaged P-47 seconds to ever make it home, described the psychological confidence the aircraft's capabilities provided. "Knowing you could dive away from any threat changed how you fought. You could press attacks longer because you had an escape route that was guaranteed. You could take calculated risks because even if you made a mistake, you could dive away at speeds nothing could match. The turbocharger didn't just make us faster at altitude. It made us braver in combat because we knew we had options other fighters didn't have." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical sophistication of the turbocharger system becomes even more impressive when examining its automatic control mechanisms. The turbocharger had to operate across an enormous range of altitudes and speeds, from sea level to over 40,000 feet, from idle power to war emergency power, all while maintaining precise boost pressure control to prevent engine damage. This was accomplished through an ingenious mechanical control system designed by General Electric engineers. The system used an oil-operated wastegate valve that could partially or fully bypass exhaust gases around the turbine. When the engine needed maximum boost at high altitude, the wastegate closed completely, directing all exhaust through the turbine to spin it at maximum speed. As the aircraft descended and air density increased, the wastegate would automatically open to bypass some exhaust, preventing overboost that could destroy the engine. The pilot controlled this entire system with a single lever, the throttle. Moving the throttle forward signaled more power, and the automatic control system would adjust turbocharger speed, wastegate position, mixture, and propeller pitch to deliver the requested power safely across the entire flight envelope. This automation was revolutionary for 1943. Most turbocharged engines required pilots to manually manage multiple controls, making them too complex for combat operations where pilots needed to focus on fighting rather than engine management. The reliability of this system under combat conditions proved exceptional. Unlike the mechanically complex German engines with their multiple speed superchargers requiring manual gear changes, the P-47's turbocharger worked automatically and rarely failed. Maintenance records from the 8th Air Force show that turbocharger-related failures accounted for less than 3% of all P-47 mechanical issues, despite the system operating under extreme temperatures and stresses. This reliability had enormous strategic implications. Units flying P-47 seconds could maintain higher operational readiness rates because their aircraft spent less time undergoing maintenance. During the critical months of 1944, when the 8th Air Force was conducting maximum effort bombing campaigns into Germany, P-47 groups consistently maintained operational readiness above 75%, meaning 3/4 of their assigned aircraft were combat-ready on any given day. This compared favorably to German fighter units, which struggled to maintain 50% readiness due to maintenance issues and spare parts shortages. The weight penalty of the turbocharger system, approximately 800 pounds, including ducting, oil systems, and controls, and had been the primary argument against the design during the P-47's development. Critics correctly noted that this weight could have been saved by using a conventional engine-driven supercharger, making the aircraft lighter and more maneuverable. What these critics failed to appreciate was that the high-altitude performance and diving capabilities enabled by the turbocharger were worth far more tactically than improved maneuverability would have been. Combat statistics validated this judgment decisively. During calendar year 1944, P-47 units in the 8th Air Force achieved overall kill ratios exceeding 5-1, and when examining only high-altitude engagements where proper tactics were employed, these ratios climbed above 10-1. The 56th Fighter Group, the top-scoring P-47 unit with 674.5 confirmed victories, achieved a kill ratio of 11.2-1 when considering only aircraft lost in air-to-air combat. These statistics weren't just numbers. They represented German pilots who died because they couldn't effectively counter American tactics enabled by turbocharged high-altitude performance. They represented bomber crews who survived because P-47 escorts destroyed attacking German fighters before they could press home their attacks. They represented strategic bombing missions that succeeded in destroying German oil production, aircraft factories, and transportation networks because fighter escorts achieved air superiority. The psychological impact on Luftwaffe pilots of facing an enemy with unmatched diving performance and altitude advantage appeared repeatedly in captured German documents and post-war interviews. Tactical directives issued by German fighter wings in late 1943 and early 1944 showed increasing concern about engaging American fighters at high altitude. Some units explicitly instructed pilots to avoid combat above 25,000 feet, conceding the high-altitude environment entirely to American fighters. Oberst Johannes Steinhoff, who commanded Jagdgeschwader 7-7 and survived the war with 176 victories, provided insight into German tactical thinking in his 1970 memoir. The American Thunderbolts presented a unique challenge. They could choose when and where to fight. If they held altitude advantage, they were nearly invulnerable to our attacks. We could only hope they would make the mistake of coming down to our altitude where we had advantages. But their pilots were well trained and disciplined. They stayed high, dove only when they had perfect position, then climbed away before we could respond. It was frustrating beyond description. We had faster aircraft at low altitude, better turning fighters, experienced pilots. None of it mattered because we couldn't force them to fight on our terms. The winter of 1943-44 brought the apex of P-47 diving tactics. By this point, American pilots had accumulated hundreds of hours of combat experience, doctrine was well established, and the turbocharger's capabilities were fully exploited. Missions deep into Germany encountered massive Luftwaffe formations, attempting to stop the bomber streams through sheer numerical superiority. These engagements tested whether the altitude and diving speed advantages of the P-47 could prevail against determined, experienced German pilots flying excellent aircraft. The mission of January 11, 1944, provided a definitive answer. The 56th Fighter Group escorted B-17 bombers to Oschersleben and encountered over 100 German fighters, including crack units equipped with heavily armed and armoured FW-190s specifically designed for bomber destruction. The battle lasted over an hour and ranged across 150 miles of German airspace. Major Francis Gabreski, leading the escort formation, positioned his flights at 29,000 feet, maintaining 6,000 feet altitude advantage over the bomber stream. When German fighters began their attack runs on the bombers, climbing from airfields across central Germany, the P-47's Dove. Report after report from participating pilots described the same sequence. Roll inverted to keep the target in sight. Pull 4 to 5G to point the nose downward at 45 to 60 degree dive angle. Advance throttle to maximum power. Watch the airspeed indicator climb past 400, 420, 450, approaching or exceeding 500 miles per hour. At these speeds, the P-47 closed on German fighters so rapidly that evasive action was nearly impossible. The massed firepower of 8 50 caliber machine guns firing armor-piercing incendiary rounds at convergence ranges between 300 to 400 yards destroyed or severely damaged. Enemy fighters with short bursts of 2 to 3 seconds. Then, before any other German aircraft could maneuver to counterattack, the P-47 pilot would pull back firmly, zoom climb back above 27,000 feet, and be repositioned for another attack within 1 minute. The 56th Fighter Group claimed 22 confirmed victories that day for the loss of 4 aircraft. The 4-to-1 exchange ratio seems modest compared to some individual engagements, but it represented a strategic catastrophe for the Luftwaffe. They were losing experienced pilots at a rate that training programs couldn't replace, while American pilot production was expanding and producing increasingly well-trained aviators. More significantly, the bombers suffered minimal losses during periods when P-47 escort was present. Only 5 B-17s were shot down while under direct P-47 protection, compared to much higher losses on portions of the route where fighters had to turn back due to fuel limitations. This protective success was the true measure of tactical effectiveness. The P-47s weren't primarily designed to shoot down German fighters. They were designed to protect bombers, so those bombers could destroy Germany's capacity to wage war. The Turbocharger enabled this protection by allowing P-47s to maintain position above the bombers, where they could see all threats developing and respond before German fighters could press home attacks. Traditional fighter escorts, forced to fly at bomber altitude due to engine limitations, were vulnerable to German fighters attacking from above. The P-47's turbocharged altitude advantage inverted this tactical problem. German fighters had to climb through the escort layer to reach bombers, exposing themselves to diving attacks during their most vulnerable phase. By spring 1944, the Luftwaffe's day fighter force had been effectively broken. They could still mount formidable resistance, but no longer in sufficient strength or with sufficient tactical advantage to seriously threaten the bomber streams. German fighter production was actually increasing during this period, with monthly production reaching all-time highs, but experienced pilots were irreplaceable, and the kill ratios achieved by P-47 and other American escort fighters meant the Luftwaffe was suffering unsustainable losses. The turbocharger's contribution to this strategic victory is difficult to quantify precisely, but was undeniably significant. Without turbocharged high-altitude performance, American escorts would have been forced to fly at bomber altitude or only slightly above, eliminating the altitude and diving speed advantages that made their tactics so effective. German fighters would have been able to engage on more favorable terms, increasing American losses and decreasing their ability to protect bombers effectively. The technical evolution of the P-47's turbocharger system continued throughout the war, with each variant incorporating refinements based on combat experience. The early P-47B and C models used the General Electric Type B2 turbocharger with a maximum turbine speed of 20,000 revolutions per minute. Combat experience revealed this was insufficient for optimal performance at extreme altitudes, leading to the Type B11 turbocharger introduced on P-47D variants. The B11 turbine could safely operate at 21,300 revolutions per minute, providing approximately 8% more boost pressure at critical altitudes above 30,000 feet. This seemingly modest improvement translated to approximately 150 additional horsepower at 30,000 feet, enough to increase maximum speed by 12 to 15 miles per hour and climb rate by approximately 200 feet per minute at altitude. In tactical terms, this meant P-47D aircraft could maintain altitude advantage more easily and execute their zoom climbs with greater energy reserve. The most sophisticated variant, the P-47M, introduced in late 1944 specifically for intercepting German jet aircraft, utilized an uprated R2-80057 engine with improved turbocharger, producing 2,800 horsepower at war emergency power. This variant could achieve 470 miles per hour in level flight at 30,000 feet and could dive to indicated airspeeds approaching 600 miles per hour under ideal conditions, though compressibility effects at these extreme velocities made control challenging even for the massively strong Thunderbolt. The P-47M's performance proved sufficient to catch and destroy Mi-262 jets if the jet pilot made tactical errors or was caught during takeoff or landing, when jet engines of that era were particularly vulnerable. However, the war ended before P-47Ms saw extensive combat, and only about 130 were produced. Their existence nonetheless demonstrated how far turbocharger technology had advanced, enabling piston engine fighters to remain competitive even as jet propulsion emerged. German engineers, studying captured P-47 seconds at testing facilities in Reich, expressed professional admiration for the turbocharger installation. Their technical reports, discovered in archives after the war, acknowledged that General Electric and Republic Aviation had solved integration problems that German designers had deemed unsolvable. The primary German concern had been reliability. They assumed the extreme temperatures and rotational speeds would cause frequent failures unsuitable for combat operations. What German engineers discovered upon examination contradicted their assumptions completely. The turbocharger system was not only reliable but required minimal specialized maintenance. Standard engine maintenance procedures covered the turbocharger. The automatic control system meant pilots didn't need extensive additional training. The entire installation represented American industrial engineering at its finest. Complex capabilities delivered through systems that were practical, maintainable, and suitable for mass production. This last point proved strategically decisive. Germany produced excellent turbocharged engines, including the Jumo 213 that powered late-war Focke-Wulf variants and delivered impressive high-altitude performance. But German turbocharger technology never matched American reliability or ease of production. German turbocharged engines required specialized maintenance, frequent component replacement, and careful pilot management. They were suitable for limited production, experimental aircraft, but not for the mass-produced frontline fighters Germany desperately needed. The United States, by contrast, produced over 15,000 P-47 seconds with turbocharged engines, every one capable of the high-altitude performance and diving tactics that proved so effective. This mass production of advanced technology exemplified American industrial advantages. It wasn't sufficient to invent sophisticated systems. Victory required producing those systems in quantities that could overwhelm the enemy through sheer numbers, combined with qualitative superiority. The personal accounts from pilots who flew diving attacks enabled by turbocharged performance reveal the human dimension of this technological advantage. Captain Gerald Johnson, who scored 22 victories flying P-47 seconds with the 56th Fighter Group, described the experience in interviews conducted during the 1980s. The dive was the most intense moment of every mission. You would roll inverted, looking down through your canopy at the ground 6 miles below. Then you would pull the stick into your stomach and point straight down at the earth. The engine would roar as the turbocharger kept feeding it air. The airspeed would build incredibly fast. Your aircraft would start shaking from the speed. You had to trust the engineering, trust that Republic built this machine strong enough to handle what you were doing to it, Johnson continued. At 500 miles per hour, you were moving so fast that everything happened in seconds. You would see your target growing larger incredibly rapidly. You had maybe 2 seconds to line up, Fire your burst, then pull. The pull-out was the hardest part physically. 6. 7G, pushing you down into your seat. Your vision would tunnel. Sometimes you would grey out briefly, but you held that back pressure, and the aircraft would pull through every time. Then you would be climbing, using all that speed to get back up high where you were safe. The whole sequence from starting the dive to being back at altitude took less than 2 minutes. The Germans never figured out how to counter it. The physical toll of repeated high-speed dives and high-G recoveries accumulated over combat tours. Pilots frequently reported back pain from spinal compression during pullouts, vision problems from repeated G-induced strain on blood vessels, and general physical exhaustion after missions involving multiple diving attacks. Squadron medical officers monitored pilots closely for signs of cumulative G-force damage, occasionally grounding pilots temporarily to allow recovery. Yet despite these physical hardships, pilot morale in P-47 units remained exceptionally high throughout the war. The confidence that came from flying an aircraft with overwhelming tactical advantages, combined with the Thunderbolt's legendary survivability when hit by enemy fire, created a psychological environment where pilots felt they had the tools needed to survive and succeed. This confidence translated directly into aggressive tactics and better combat performance. German pilots experienced the inverse psychological effect. By mid-1944, Luftwaffe fighter pilots increasingly reported feelings of helplessness when engaging American fighters at high altitude. They could see the Thunderbolts above them, knowing an attack could come at any moment from any direction at speeds they couldn't match. They knew that climbing to engage the Americans would expose them to diving attacks during the climb, and even if they reached high altitude, the P-47 seconds would simply climb higher. Luftwaffe combat reports from this period show increasing use of phrases like enemy fighters approached from above at high speed, or unable to evade diving attack. German pilots were acknowledging that American tactics based on altitude superiority and diving speed had created a situation where German fighter performance advantages at lower altitudes became irrelevant. The battle was being fought on American terms, in the high-altitude environment where turbocharged engines gave P-47 seconds unmatched capability. The strategic bombing campaign's success in 1944 depended absolutely on achieving this air superiority. Between February and June 1944, the 8th Air Force flew deep penetration missions against German oil refineries, aircraft factories, and transportation networks. These missions destroyed Germany's ability to fuel its military machine, train replacement pilots, or move forces effectively. But these missions succeeded only because fighter escorts, particularly turbocharged P-47 seconds and long-range, P-51 seconds, achieved and maintained air superiority over Germany. The P-47's contribution to this air superiority was disproportionate to its numbers. While P-51 Mustangs eventually outnumbered Thunderbolts in escort roles due to their superior range, P-47 seconds continued flying the most dangerous missions: initial penetration escort where German fighter opposition was strongest, close escort during bombing runs where anti-aircraft fire was heaviest, and suppression missions against German airfields where ground fire threatened any aircraft operating at low altitude. The Thunderbolt's turbocharged power and structural strength made it ideal for these high-risk roles. The aircraft could fight effectively at any altitude from ground level to over 40,000 feet. It could absorb battle damage that would destroy lighter fighters. And critically, its diving speed gave pilots an escape option in any tactical situation. Pilots flying these dangerous missions knew they were flying the right aircraft for the job. By the time Germany surrendered in May 1945, the P-47 had compiled a combat record that validated every engineering decision that went into its design. Over 546,000 combat sorties in the European and Mediterranean theatres, 3,752 confirmed air-to-air victories, approximately 3,000 more enemy aircraft destroyed on the ground, a combat loss rate of 0.7% per sortie, the lowest of any American fighter, and most importantly, Thousands of pilots who came home alive because they flew an aircraft that could outfight, outrun, or survive anything the enemy could throw at it. The turbocharger system, that 800-pound collection of ducting, turbines, controls, and intercoolers that critics had called an unnecessary weight penalty, had proven to be the single most important system on the aircraft. It enabled the high-altitude performance that gave American pilots altitude advantage. It enabled the diving speeds that made attacks nearly impossible to evade. It enabled the zoom climbs that provided defensive escape and offensive repositioning. Without the turbocharger, the P-47 would have been just another heavy fighter with mediocre performance. With the turbocharger, it became the aircraft that helped achieve air superiority over Germany. The post-war interviews with German aces consistently acknowledged this technological advantage. When asked what Allied aircraft they most respected or feared, many German pilots mentioned the P-47 specifically because of its performance at altitude. Oberstleutnant Günther Rahl, third highest scoring ace in history with 275 victories, provided perhaps the clearest technical assessment in a 1973 interview with an American aviation magazine. The Thunderbolt at high altitude was essentially unbeatable if the pilot followed proper doctrine. We understood what they were doing. We knew they were using altitude advantage to enable high-speed diving attacks. We knew they were using superior engine performance at altitude to maintain that advantage. But knowing their tactics didn't help us counter them. Our engines couldn't produce the power at high altitude that theirs could. We couldn't dive as fast safely. We couldn't climb back up as quickly. The technical advantage they had from their turbocharger system created a tactical advantage we simply couldn't overcome with pilot skill or tactical innovation, Rahl continued. Some of our pilots tried various counter-tactics, attack the bombers from below where the P-47 seconds couldn't dive on you as easily, stay at very low altitude where our engines had power advantage, refuse to climb to high altitude at all. None of these tactics worked well. Attacking from below exposed you to bomber defensive fire. Staying low meant you couldn't effectively attack bombers at all. Refusing to climb meant surrendering the Pernik, entire high-altitude environment to American fighters. The Americans had created a system where they controlled the fight from start to finish. The turbocharger was the key to that system. This acknowledgement from one of Germany's greatest fighter pilots represents the ultimate validation of the P-47's design philosophy and the critical role of its turbocharger system. The technical advantage created by turbocharged high-altitude performance translated directly into tactical dominance, which translated into strategic success for the Allied bombing campaign, which contributed significantly to Germany's defeat. The engineering legacy of the P-47's turbocharger system extended far beyond World War II. Post-war analysis by the United States Air Force concluded that turbocharged or jet-powered high-altitude performance was essential for future fighters. The era of naturally aspirated engines optimized for low to medium altitude was over. Every subsequent American fighter incorporated either turbochargers, turbojets, or later turbofan engines that provided high thrust at all altitudes. The Korean War provided additional validation when Francis Gabreski, the P-47 ace from World War II, flew F-86 Sabres against MiG-15 seconds. The jet engines in both aircraft provided good power at all altitudes, creating a more balanced tactical environment than had existed in World War II. But the fundamental tactical principle remained valid. The fighter with energy advantage, whether from altitude, speed, or both, controlled the engagement. Gabreski shot down 6.5 MiG-15 seconds in Korea, applying the same energy management principles he had learned in turbocharged Thunderbolts over Germany. Modern fighter aircraft continue to emphasize high-altitude performance and energy management. The F-15 Eagle, F-16 Fighting Falcon, and F-22 Raptor all feature high thrust-to-weight ratios and excellent high-altitude capabilities that allow them to control engagements through energy advantage, exactly as P-47 pilots did 8 decades earlier. The specific technology has changed from turbochargers to advanced turbofans with afterburners, but the tactical principle remains constant. Control the vertical dimension of combat, and you control the battle. The handful of airworthy P-47 that remain, carefully maintained by museums and collectors, still demonstrate the capabilities that made them so effective. At airshows, these 70-year-old aircraft perform high-speed passes and climbing maneuvers that showcase the power of their turbocharged engines. The distinctive sound of a Pratt & Whitney R2800 at full power, with its turbocharger whistling at maximum RPM, is unmistakable to anyone who has heard it. That sound represented terror to Luftwaffe pilots who heard it diving toward them from above. It represented confidence and safety to American bomber crews who saw P-47 patrolling overhead, and it represented the sound of American engineering excellence translated into WWII, tactical dominance. The story of the P-47's turbocharger system and the diving tactics it enabled demonstrates a fundamental truth about warfare and technology. Superior technology alone doesn't guarantee victory. The technology must be matched with tactics that exploit its advantages and training that ensures proper execution. The Germans had excellent aircraft and supremely skilled pilots, but American engineers created a technological advantage through the turbocharger system. American tacticians developed doctrine that exploited that advantage, and American training programs produced pilots disciplined enough to execute the tactics correctly. This combination proved unbeatable. German pilots would report hitting Thunderbolts with cannon fire, only to watch them dive away at speeds nothing could match. They would watch American fighters climb back to altitude using power their engines couldn't produce at high altitude. They would experience the frustration of fighting an enemy who could choose when and where to engage, always attacking from a position of overwhelming advantage, always escaping before effective counterattack was possible. The turbocharger made all of this possible, that 800-pound system buried in the rear fuselage, spinning at over 21,000 revolutions per minute, channeling exhaust gases and compressing thin air, maintaining sea-level power at 30,000 feet. That was the secret weapon German pilots never understood until it was too late. They could see the P-47 diving at impossible speeds. They could see them climbing away at rates German fighters couldn't match. But they didn't know about the turbocharger. They didn't understand the engineering that made those capabilities possible. By the time German intelligence fully understood the P-47's turbocharger system and its tactical implications, the strategic situation had deteriorated beyond recovery. The Luftwaffe had lost too many experienced pilots. German oil production was being systematically destroyed, limiting flight training and combat operations. Allied air superiority was absolute. The technical knowledge came too late to matter. The final assessment belongs to Colonel Hubert Zemke, who commanded the 56th Fighter Group during its most successful period and established the tactical doctrine that made P-47 so effective. In his post-war memoir, written 4 decades after the events, Zemke reflected on what made the Thunderbolt successful. The P-47 was not a forgiving aircraft. It was heavy, it was complex, it required proper technique to fly effectively. But if you flew it correctly, if you used its strengths and avoided its weaknesses, it was unbeatable. The turbocharger gave us high-altitude performance that nothing could match. That altitude advantage let us dive on the enemy at speeds they couldn't achieve. The dive gave us the element of surprise and overwhelming firepower concentration. The zoom climb got us back to Cullisis, safety before they could respond. The entire tactical system depended on that turbocharger, keeping our engine producing power, where German engines were gasping for air. The Germans never knew how central that system was to our success. They thought we were just better pilots or had superior numbers. The truth was simpler. We had better engineering. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.